Alright, let's talk about nuclear reactions and how we go about balancing specifically nuclear reactions. The way this ultimately works out is that you start with an element, specifically an isotope, and that isotope either reacts with another particle or it itself decays into other particles. Now, the idea behind nuclear reactions is that the atomic masses or the numbers on the bottom left corners, they have to add up to the same number on either sides of the equation. And for the masses, the same idea holds true. The sum of the masses on the left side have to equal the sum of the masses on the right side. And this is kind of like, in some ways, the corollary of conservation of mass. Although, as I told you before, you don't necessarily conserve mass because it can be transferred to energy. But for the purposes of nuclear reaction balancing, we're going to still hold that premise true. So the sum of the reactants, for either the top rows or the bottom rows have to equal the sum of the products for the corresponding top row or bottom row. So what this means is that if you start with an element with an atomic mass of A, the sum of A sub 1 and A sub 2 has to equal the value of A. And the same thing goes for Z. Z will have to equal Z sub 1 and Z sub 2 in order for this to be balanced correctly. Alright, so with that premise, we're going to start the process of talking about the individual nuclear processes that take place. We're going to start with alpha emission. And here's where you have to keep in mind what the different particles are. So in alpha emission, you're going to be producing an alpha particle. And the alpha particle is a helium-4 isotope, right? And you have the atomic number being 2 because this is helium, but that's the alpha particle. So that's what's alpha emission. If we keep the isotope on the left completely symbolical, then or symbolic, we can actually write this in symbolic format as well. The value of Z for the left side of the equation has to be equal on the right side. So that means that the new element that you may be missing has to end up with an atomic mass of Z minus 2, because Z minus 2 plus 2 will equal Z. And for the atomic mass of the new element, A minus 4 will have to be the mass of this element. And right now, it may start looking kind of ugly, but as you'll see, you won't necessarily have to write these equations down. You'll just do the math, sometimes maybe even in your head, so you don't even need to write down all of these things symbolically. But the key idea is that the mass number will go down by 4 units, and the atomic mass of the element will go down by 2 units. This is simply because you have to eject an alpha particle out of the original nucleus. So let's take a look at some examples. We're going to start with plutonium. Oh, and by the way, an element that has a really high atomic number, there's a good chance, and by that I mean greater than 85, there's a really good chance that alpha emission may be happening. But nonetheless, I can tell you, predict the products of alpha emission for this isotope. So here, we'll start with plutonium-239 and say, okay, we'll produce the alpha particle. And yes, plutonium-239, that's, by the way, element 94. And we know that because this is plutonium. Alright, so we'll be producing an alpha particle, which means that we have to write as a product helium-4 as one of the products. And now we're going to do the math to figure out what the missing element is. Alright, so we write X for the element. We don't know what it is yet, but we're going to use the math to figure it out. The overall atomic mass on the left side is 94. We already have 2 on the right side, so that means that the missing number has to be 92, because 92 plus 2 equals 94. And likewise, for 239 being the total mass number on the reactant side, we only need to have 235 for this element in order to end up with 235 plus 4 equaling 239. So looking at the periodic table, we're looking at element 92. And in the table, element 92 is uranium. And so what you can see is that undergoing alpha emission basically moves you 2 units to the left in the periodic table as far as the element you're dealing with. Alright, so that's one example. Let's do another one. Here we have radon 219 undergoing alpha emission. So you'll have the helium particle being produced. Alright, now because the atomic number of helium is 2, and the atomic number of radon is 86, that means that the new element will have to be 84. And likewise, since the mass number is 219 for radon and the mass number of helium, the alpha particle is 4, that means that we have to end up with 215. Alright, and at this point, all you have to do is look at the periodic table and look for element 84. Element 84 is, in fact, polonium. So you now input the actual symbol for that. So polonium 215. Alright, let's do another example. We have gold 79, which will undergo alpha emission. So we'll write the helium particle at the end. And once again, for the missing element, the total mass is 79. We already have a mass of 2 for helium, so the mass here has to be 77. Excuse me, the atomic number. For the atomic mass, we have 172, 4 for helium. If you subtract them from each other, you should find out that the residual is 168. Alright, so 168 plus 4 equals 172. That's what you want to see in terms of balancing the equations. And looking at the periodic table, element 77 is none other than iridium. So you want to input iridium as the symbol for the element. Alright, one more. Americium 241. If americium undergoes alpha emission, you end up producing an alpha particle. And because of the numbers, that means that the atomic number for the missing element has to be 2 less than that of americium. So in other words, 93. And the mass number of the missing element has to be 4 less than the mass number of americium 241. So we're talking about 237. Alright, so now we'll look at the table. Element 93. If you look at the periodic table, element 93 is neptunium. So you input the symbol for neptunium right here, and with that, you're basically done. Alright, so that's alpha emission. You produce an alpha particle and you use the mass and atomic number of the alpha particle to determine what the missing element is, the missing isotope. Alright, now let's take a look at beta emission. In beta emission, you will actually be producing a beta particle, aka the electron. So the electron is being produced in the process of this nuclear reaction. And this is not to be confused with you ionizing an atom. This electron specifically is becoming a thing. It's arising from the nuclear process. So it wasn't there to begin with. It's now there because of the nuclear reaction that took place. So you'll be producing an electron. And the thing about it is that now, because we have that -1 charge for the electron, what's going to happen is that the atomic number that needs to equal Z on both sides still needs to be Z. So the only way to make that happen is to add 1 to the atomic number. So in essence, you will be raising the atomic number by 1 when you undergo beta emission. The mass of the electron is 0, so that means that the atomic mass of the new element will be identical to the original isotope you started with. Alright, so in beta emission, you're going to increase the atomic number by 1 unit. That's what ends up happening. Alright, so, and I'm going to also say something more in respect to it, but let's do a few examples of balancing. So let's say we have silicon 33, which undergoes beta emission. With that knowledge in mind, you will place the beta particle on the product. And because the atomic number is 14 for silicon, you need to end up with an atomic number of 15 for your new particle. The mass number is 0 for the electron, so automatically you just write down the mass number for silicon here for the new particle. And if you look at the table, you're basically moving 1 unit to the right. So now you're dealing with element 15, also known as phosphorus. Alright, so that will be the process. Alright, here we're going to do another one, zinc 75. For zinc 75, if we undergo beta emission, first we write the electron on the product side. And because of the minus charge of the electron, the mass number is going to go up by 1 unit from 30 to 31. The atomic number, excuse me, the mass itself, the mass number will remain constant, 75. So looking at the table, that basically takes us from zinc to gallium. So this is the element in question, element 31. Okay, here goes yet another example. We have antimony 125 undergoing beta emission. And the missing electron will have to be 51 plus 1, right? So 52, because we know that 52 minus 1 equals 51. And the mass number will be 125. If we look for element 52 on the table, we find out that it's actually tellurium. Once again, we're shifting 1 column to the right. So now we have tellurium. All right, one more, neodymium. Neodymium 149, if it undergoes beta emission, you have your electron being produced. You will look at the numbers. You have 60 for neodymium. The atomic number for X will have to be 61, and the mass number remains 149. So element 69, which is right next to neodymium, is promethium. So you input the symbol for promethium in the table. Okay, the last thing that I want to say is that here is where that antineutrino comes in. Technically speaking, it doesn't change any of the numbers on top or on the bottom because the charge and the mass of the neutrino are both zero. But it is in the process of beta emission that you produce an antineutrino, and the antineutrino goes hand in hand with the electron. So because the electron is not coming from the atom, the neutral atom itself, but it's actually being produced by the nuclear reaction itself, you have to have this antineutrino there. So this is something to keep in mind. So technically speaking, each one of these equations should have the antineutrino associated with them as products. All right, in the next video, I'm going to talk to you about positron emission, electron capture, and possibly fission and fusion. So see you then.